Hey folks, we're coming to the end of Unit E, a big long unit talking about estimation and confidence intervals. Now we want to talk about how to make a confidence interval for a population proportion. So let's take a look at what we've got here. Up until now, we've only discussed confidence intervals for the population mean. And in fact, we can construct a confidence interval for any population parameter. The other one that we've been looking at here is the binomial P, the proportion of, say, Canadians who believe something. And so here's an example here. The recent Canadian census found that 26.4% of Canadians 15 or older have never been married. Now, that's census data, which StatsCan has gathered from the last census, but what if we don't have access to the resources of Stats Canada, and so we want to find out, say, how many Canadians believe that Elvis is still alive and rocking, which is what we saw back in the end of Unit I. So we found out that 10% said that they believe that he's still alive and rocking. We'll take a quick look at that a little bit later. So we can estimate the P, the proportion, which is just really a binomial proportion from Unit B. And so you either believe that Elvis is alive and rocking or you don't. And you can take a look here at whether you're single or, in this case, never been married or not. And that's what this particular P is here. At the end of Unit N, we talked about using the normal distribution to approximate binomial probabilities. And so that's what we're going to build on here, is using actually a standardized normal or Z distribution to construct our confidence interval. So it actually looks like this. This is a 95% confidence interval for the binomial P, the proportion. So here you've got P in the middle here, and then it's got this part right here. What I want you to note is that although altogether it looks kind of ugly, just like the one for the mean did, it actually breaks down to the same three parts that we had before. So this particular guy down here is the point estimate. And just like we had X bar, which was the sample mean, this is going to be the sample proportion. So that's what that is there, is the sample proportion. And then, of course, we've got the margin of error. And the margin of error, so it's always the point estimate plus or minus a margin of error. And the margin of error is comprised of two parts. And this part here, of course, is based on the level of confidence. And then this part here is the standard error. In this case, the standard error of the proportion. Now, generically, we call that the standard error of the estimate. But if you're estimating the mean, it would be the standard error of the mean. If you're estimating the proportion, it would be the standard error of the proportion. And so down here, we've got the standard error of the estimate. And so it would be this guy here. Or, of course, you could have an FPC factor tacked onto it as well. Now, where does that come from? Well, it actually comes from this formula here. Remember, our usual standardization formula is x minus mu over sigma. But we said that for a binomial distribution, mu is equal to n times p, and sigma is equal to the square root of n times p times 1 minus p. What if we were to divide the top and bottom by n? So that's what I've done here, is x over n minus np over n gives us this here. And then if we divide this by n, so we've got n here, we would end up with this expression right here. And this guy here is what we're going to call p bar, which is the sample proportion. And this is the population proportion which we're trying to estimate. So if we were to solve for that, we'd get this guy up here in the middle of the page here. One thing to note here is if you take a look at the bottom, we've got p times 1 minus p over n. And so when we're talking about a confidence interval, of course, we don't know what p is. That's the whole point, is that we're coming up with a confidence interval for the population proportion. So what we use down there is the p bar values in the denominator. And then if we were to solve for p here, that's what we would get up here, is right in here. So p is plus or minus this and this. So, excuse me, that's how the formula is derived from really a formula which we've seen before. At the end of unit n, the normal approximation to the binomial. It is important to note that this only works, I think I've got this at the top of the page here, if n times p is at least 5 and n times 1 minus p is at least 5. Now, this will be p bar in this particular case, because of course we don't know what p is. We're estimating it, constructing a confidence interval for it, so we use p bar there on that. And that came from the normal approximation of the binomial, if you recall, at the end of unit n. So that's how we do the thing. Let's run through a problem now. And so we have E26, number 14. A company wishes to estimate the proportion. When you see the word estimate, that means you're looking for a confidence interval. It's a dead giveaway. The proportion, of course, is p. So we're trying to figure out p. So not mu, it would say estimate the mean. In this particular case, then it's estimate the proportion. So it's a confidence interval for p. The proportion of the employees who went on sick leave during the past 6 months. Now, I don't know why they can't just pull up the HR records, but this is what we've got. So we take a random sample, little n then, right, because this is a sample of 28 employees was taken, and 10 of them, that's actually our number of successes in a binomial experiment, went on sick leave. Construct a 95% confidence interval for the proportion. So what we've got here then is n is equal to, sorry, let's write this down in terms of that this is binomial in nature. And the n is going to be equal to 28, and we don't know what the p is. That's what we're trying to figure out here. So we have a p bar is equal to number of successes in the sample, x over n. And so that's equal to 10 divided by 28. And in your calculations, I would always take this to about 3 decimal places. What do we get here? It's actually to 4 decimal places. It's to 0.3571. Now, at the very end here, we'll round to 2 decimal places. But for intermediary calculations here, you want to take it to 3 or 4 decimal places. We are looking for a 95% confidence interval for p. So that's what we know at this particular point. Step number 2 is the flow chart. So let's take a look at the flow chart. And that's back a few pages here. I think it's about right here. Well, that's the t-distribution. We'll need that one later. Actually, we won't need it for this kind of problem. Where are we here? There we are. Okay. The top flow chart is when we're talking about hypothesis tests and confidence intervals for the mean. This is the guy that we want here. This is for proportion. So we can actually write proportion here. When you print off your formula sheet and you're bringing this to the exam, you can actually write in these blue things up here. You can put down the word proportion here. So you can put in some minor notes that would help you to understand this a little bit better. All right, first question. This is actually your check. Remember the check that we were talking about is n times p at least 5 and n times 1 minus p at least 5. When we're talking a hypothesis test, which we'll look at in Unit H, it will be a hypothesized p. But with a confidence interval, it's the p bar, the sample. So is n times p bar at least 5 and n times 1 minus p bar at least 5. Let's take a look at that there. Oops, went a little far. Okay, here we are, page 203. I got to remember that. Okay, so what we've got here then is we're going to do a check, and please write down this check. Is n times p bar greater than or equal to 5? And so in our particular case, that's going to be n is 28 times p bar was 10 over 28, so that comes to 10. Check. Is n times 1 minus p bar greater than or equal to 5, and that would be 28 times 18 over 28. Check, check. So the first box that we have here then works. So we've got where's our flow chart there? So we're good here. So the only other thing we have to ask is big N known? And in this particular case, it doesn't say anything here about big N. So that means then that we're down here to number 5, which is this p bar plus or minus the z value times square root of yada, yada, yada. And the difference between 5 and 6 is just the FPC factor. All right, so let's go back. Let's continue on there. So that's formula number 5. So step number 2 is that we're going to end up with formula number 5, and that is the endpoints for the confidence interval will be p bar plus or minus z alpha over 2 times the square root of p bar times 1 minus p bar over n. And again, you've got your 3 parts here. You've got your point estimate and your margin of error, which is itself broken into 2 parts here. Level of confidence associated with the z value, and then the standard error of the proportion. Step number 3. We just need to figure out this guy. And so this would be a z, let's see, a 95% level of confidence means that alpha will be equal to 0.05. Alpha over 2 is equal to 0.025. So we're looking for a z of 0.025. We've actually done this a couple of times. It's 1.96. And so that's the z value that has 2.5% in the tail, 47.5% in the middle of the table, which you would look at, or you could look on a t-table at the bottom of a 2.5% column, and you would find 1.96. If you're having trouble with that, go back and take a look at a couple of the last videos there, and it will help you to see that 1.96, but it's something that we've seen before. All right, let's plug these numbers in. So step number 4 here then is where we take all these and we plug them in. So we're going to have p bar, which is 0.3571, plus or minus 1.96 times the square root of 0.3571 times 1 minus 0.3571 over n, which was 28. And that's going to give us 0.3571 plus or minus, and sorry, I'm just going to write that a little higher because I need to get the answer in there. So that's going to be 0.3571 plus or minus 0.1775. And that's going to give us a lower bound here of 0.1796, 0.1796, and 0.5346, which we're going to take to a couple of decimal places. So the last thing that we do here is to write our answer. And again, I'm going to show you 3 ways. You only have to show one way. And so if a probability statement does it, then that's good. Just make sure that you write the probability statement correctly. I'm going to take this to 2 decimal places. So it's 18%. The thing in the middle is a P, not a P bar, right? P bar is like an X bar. It's a point estimate. We use the P bar to estimate the P, just like we use the X bar to estimate a mu. So make sure that you got a P in the middle, not a P bar. And then we've got 53 here, and that is 95%. So that is what we've got. That is completely fine as an answer. If I told you to write this in words that a non-statistician would understand, I'd expect you to write the words. So we are 95% confident, very sure, that the proportion of employees who went on sick leave in the last 6 months is, is between 36% and 53%. So you can come up with a confidence interval, but we've only sampled 28 employees. So that's why we've got such a large margin of error here. It's an 18% margin of error. And so it'd be better actually to sample more employees if you can, and that would give us a smaller margin of error. Or we can write this the newspaper way. And the newspaper way is that the study shows that the portion of employees that went on sick leave is about 36%. That's your point estimate up here. Okay. That's 10 out of 28. 36%. This is accurate. With an 18% margin of error. And that's this guy right here. $19 times 20. And that is your 95% up here. So that's how we write that. Hey, I just want to go back here to about page 12 or so, 11. And again, this is the Elvis example, and I want you to see how this is written. So 10% of Canadians believe that Elvis is alive and rocking. That's the point estimate. This is accurate with a 4% margin of error 19 times in 20. So now you know what this means. It took us all course to get there, but that's exactly what we're looking at here. So we know how that works now. So with that then, I'd like you to do number 15 for homework, and we will take that up in class. And that will just leave us with one last section after this. So let's end it there.